In this video, we're going to go through a deep dive of how we can understand regression, and in particular, a very simple form, the basic form of regression, which is linear regression. So, let's talk about regression and linear regression in depth. In this video, I'm going to walk you through what it is like to use Python to implement a linear regression model from scratch. A very simple one, nevertheless. It will help you understand and visualize how data goes in and out of a linear model and how it gets created. Before we start, what we need to do is to understand certain NumPy functions that we're going to use and will appear in the linear regression model below. Number one, with numpy.concatenate, we're joining two sequences of arrays along an existing axis. This is a little bit like if you have two Python lists and you're using the add operator to add them together. np.ones returns a new array of a given shape and type filled with ones. np.zeros returns a new array of given shape and type filled with zeros. np.dots is what's called mathematically a dot product. And if you don't understand this, it's very easy. If the first argument, A, is an ND array, in our case, is a matrix, so it's a 2D array, and B, which is the second argument of the dot product, is a 1D array, or a list, then it is a sum product over the last axes of A and B. So what this means is we multiply each row of A with B, and then we add the last axes of A together. Armed with this knowledge, let's go take a look. Firstly, we want to define some high-level hyperparameters. We first define the learning rate of the linear regression optimization algorithm. We're specifying this as 0.01. We want to define whether we want to fit an intercept to this linear model, and we're calling this true. The third thing we want to define, it's a weights parameter, which stores our array of weights. So if we have two pieces of information, X, which is the features, a feature matrix has both rows and columns, which is Y, there are two dimensions. Whereas a label, which is the Y, has just one dimension because it's simply for each data point, there's a correct label. So there isn't a concept of a column. All there is the concept of rows. So we fit XY, which is a 2D matrix fitted to a 1D vector. We first want to store the weights in a global variable by declaring global on weights. In the highlighted line, we're deciding whether we need to fit an intercept. If we do, in the highlighted portion of the code, we're assigning the concatenation of a matrix filled with ones and X, which is the feature matrix, a concatenation of that along the first axis, which is the columns, into X. And we initialize the weights of the linear model as zeros with the shape of the number of columns there are in X. The effect of this is if there's no intercept, then we're going to have the weights matrix or vector to be a list of zeros that is the length of the number of features in X. And then we want to train a gradient descent optimization algorithm over a number of epochs. In the highlighted line, I'm initializing a for loop that runs 1,000 loops. Each loop via the for loop is an epoch. In the first part of the loop, I first look at the current prediction. The current prediction is a dot product, otherwise known as the sum product, of X, the features, and the weights vector. This produces a vector that is the length of Y, and we can compare this prediction vector with the correct answer. To make this comparison, we're looking at the dot product of the transpose of the feature and the difference between the current prediction subtracted by the correct answer. We need to normalize this by the scale of y, so we divide it by y dot size. In the last step, I am looking at weights and I'm subtracting from weights the learning rate multiplied by the gradient. To predict the probability of different classes, given that we're given a matrix X, we first load in the global variable that is weights. If we fit the intercept, again we need to concatenate this X with a column of 1s before X. As you might expect, the current prediction is the same thing as the first line in the gradient descent optimization loop, and so we're simply returning the dot product between X and the weights. So hopefully that wasn't too complicated, but I felt like that was quite crucial for you guys to understand. And so in the next video, we're going to talk about implementing a linear regression model to predict the seed's progression. I'll see you guys next time.